Yeah, welcome to a Massive Open online course on chemical process intensification. In this module, the mechanism of intensification, we will discuss in this lecture the intensification by fluid flow process. In the previous lecture, we have discussed something about the strategic aspect of chemical process intensification. So, based on that strategy, how the intensification in the chemical engineering processes can be carried out, that has already been discussed. So, as an extension that we can here describe something about what are the mechanism of that process intensification in multi-phase flow system. So, as you know that in our different chemical engineering processes, the different phases are directly or indirectly taking part for a particular process yield. So, in that case you have to know something about that the multi-phase flow system. So, multi-phase flow system, how it can be defined, that the multi-phase flow system can be defined as the system where the materials with different states or phases like gas, liquid and solid can be taking part for a particular process. So, that is called multi-phase flow system, and process is called multi-phase flow process. The multi-phase flow also defined in different other way, like if there are two phases immiscible to each other in a particular flow, then you can say that those phases will be different in their chemical properties. So, materials with different chemical properties, but in the same state or phase can also be referred to as multi-phase flow. In this case, remember that whenever we are processing any chemical engineering system, in that case when multi-phase are taking part for that particular process, in that case one of the phases is continuous, while the others are dispersed within the continuous phase. Like if suppose gas is dispersed in a continuous liquid phase, then we can say that gas is a dispersed phase and liquid is a continuous phase there. So, in this case gas liquid process like absorption process or some other reaction processes, also gas liquid reaction, there also these two phases will be taking part. But if that two phases will be taking place in presence of solid catalyst, then you can say here there will be a three phase flow. So, in that case the two phase may be in that case discrete, like gas and solid particles will be discrete, whereas liquid will be in a continuous phase. So, in any multiple or multi-phase flow system, you can say that one phase should be discrete and another phase should be continuous. So, we can divide this multi-phase system into two system like gas liquid system or two phase system and then three phase system. But two phase system, not only the gas liquid, there should be other like liquid solid, even gas solid system also. So, the two phase will be as like gas solid, liquid solid and gas liquid, and three phase system gas liquid solid. So, gas or liquid acts as a continuous phase there somewhere in particular processes, and gas or solid acts as a discrete or dispersed phases. Sometimes if liquid is spraying as a dispersed phase of droplets in a gaseous medium, then in that case liquid droplets will be a discrete phase and gas will be continuous phase. So, gas phase may be either in continuous or discrete, both may be there as per particular application. And let us have some application of that different multi-phase flow systems first. So, what are those gas liquid flow systems? In this case gas is used as a dispersed phase and liquid as continuous fluid, like absorption of gas in liquid to remove it from gaseous mixture. Example, mixture of COX, NOx or hydrogen sulfide etc. from polluted air in solvent. like ozonation of arsenic to arsenate, or removal of ammonia or dye in water treatment there. So, in that case gas liquid operation is most important, and also some other applications like gas liquid chromatography for analysis of liquid petroleum fractions. In that case gas liquid both are taking part in this particular analysis. Even gas liquid reactions process like industrial gases like oxygenation process, hydrogenation process, carbon monoxide and carbon dioxides, those are widely used for synthetic processes in the chemical industry to produce different type of hydrocarbons. So, in that case gas liquid systems are important. Liquid gas systems, as an example here, in this case liquid is used as discrete fluid and gas as continuous fluid. Like in a spray column, the liquid is sprayed in gaseous medium for absorption of gas, whereas spray towers can be very effective in removing pollutants if the pollutants are highly soluble in the liquids there. And also in the production of superphosphate used in manufacturing fertilizer, there also this liquid will be used as a discrete phase, and also production of silicon tetrafluoride and hydrogen fluoride gases are vented from various points in the process, where this gas liquid operations for the production of superphosphate used in manufacturing fertilizer, silicon tetrafluoride and hydrogen fluoride gases. And the spray towers are also used for odor removal in the bone metal and tallow manufacturing industries by scrubbing the exhaust gases with a solution of potassium permanganate. So, these are the some applications where liquid and gas will be taking part. In that case liquid will be discrete and gas will be continuous phase. In the gas solid system, you will see there are several applications of this gas solid system. The chemical engineering process and the heart, it can be said that the gas solid operation are the most important and diversible application in chemical industry. In that case there are several processes like physical processes and even some reactive processes, gas solid reactions are there. In physical processes like drying of particles, in that case fluidization operation is very important. Coating of surfaces, granulation, even heat treatment, and also you can say that filtration, blending and segregation or classification of the solid particles in fluidized bed. So, these are actually gas solid operations. Also in gas solid reactions like roasting of ores, combustion of coal to produce different types of hydrocarbons, even for power plant operation to produce the power there. Of course, this coal is combusted and there are different types of gaseous products are coming out, and separating those gaseous products, they are being used for several purposes, and also those are used for unwanted gas also, sometimes producing the steam by just by burning coal, and that steam will be used for or is being used for the production of power, and they are by just by rotating the turbine. So, in that case that gas solid operation is important, and also calcination and limestone phosphates, even aluminum hydroxide, fluid cracking etc. For that this gas solid operations are very useful. And also liquid system, there are several applications for this liquid system also. Liquids are used as both here discrete as well as continuous phase, like used for flow of emulsion of oil and water in pipelines. Different types of like contactors like packed bed, packed columns, pulsed columns, and star tank reactors in various applications where liquid and liquid systems are important. Also liquid extractions, solvent extractions to remove the contamination from the wastewater, the extraction of that contaminants by another liquid component or organic liquid, that is also important. So, liquid extraction is also important just to remove some contaminants from the wastewater or some other liquid medium where it will not be useful. And liquid solid system where hydraulic conveying of solid materials are there, so it is important, and in that case solid particles is dispersed in liquid, and slurry flows cover a wide spectrum of applications there that ranges from transport of coals and ores to the flow of mud. And also in crystallization you will see solids are suspended in liquid, and the flow of liquid through a solid is another example of porous media flow. So, these are the operation for the liquid solid system. In three phase systems you will see some gas liquid solid system. If you are combination of this operation of gas liquid solid, you will see in the mineral industry the flotation is one of the important process by which that metals will be separated from its ore, valuable metals will be separated from the ores. In that case you will see the flotation process important, and during that flotation this aeration is being done, and during that aeration this gas and liquid and solid both three phase will be taking part, and also sometimes some fine particles to be removed from the muddy water, or you can say that milk water where solid particles are suspended. To separate those fine particles, this flotation process also important. In that case surfactant some that frothers to be used, so that as per flotations that these fine particles will be separated by aeration. So, in that case gas and liquid and solids three phases are taking part. Other applications like fluid bed catalytic cracking in presence of some catalyst particles, hydrocracking, hydroprocessing and biochemical processes, those are involved in three phase systems. And very common flows of oil, water, natural gas, that is found in condensation or evaporation of immiscible liquid mixture. There also gas liquid systems are important, and solid liquid systems there you will see in pipelines. If sand is mixed with oil and water, the three phase flow is important there. So, these are the various applications of the three phase systems. And four phase systems also, one application like in freeze desalination process, you will see that when butane liquid is added into a saline water, that will results a formation of isocels, and in this case system is a mixture of butane liquid, water, ice and the butane vapor. These four phases are there. So, that is why four phase systems are there, it is considered. So, we have then seen that different applications of four phase systems in our daily life, whatever products we are getting, all processes by which these products are coming out are related to the multi-phase flow systems, whether it is gas liquid or liquid solid or gas liquid solid system, even gas liquid solid and vapor system, both are directly or indirectly related to their particular processes. So, based on these multi-phase flow processes, whenever we are going to perform these processes in a particular unit, that process can be intensified based on the development of the unit or equipment, or based on the fundamental like that phenomena, even sometimes the fluid phenomena, based on the fluid phenomena, based on the equipment size, based on the that policy. So, we can intensify the process in different aspects. So, in this lecture we will discuss that based on these multi-phase flow systems, what are the different mechanism of the process intensification which are being used in industry as per process intensification background. So, flow based process unit for intensification, you can say that some important chemical engineering process unit for process intensifications are like this trickle bed reactor, where liquid phase and gas phase are flowing through the packed bed, and their liquid phase will be flowing as a laminar stream, just as called trickle phenomena. So, that is trickle bed reactor. So, in that case you will see that plug flow phenomena will observe, and then reaction efficiency or that that process performance will be higher than the conventional processes for that particular process. Bubble column reactor, there also it is being developed based on the increase of or enhancement of the interfacial area of between phases. Like in bubble column reactor, if it is two phases gas liquid operations, only physical operations like carbon dioxide gas will be absorbed in a sodium hydroxide solution there. In that case, gas phase is dispersed in that column as a dispersed phase of bubbles in a continuous liquid medium here as a sodium hydroxide solution. In that case, the whenever bubbles will be forming, there will be interface between that bubbles and liquid. So, you can get that interfacial area through which there will be a mass transfer, and based on that mass transfer you can say that absorption of that carbon dioxide gas in the gaseous mixture, which will be absorbed in a liquid medium through the interface. So, if you can increase the interfacial area, you can have the more efficiency of the absorption process. So, that is why the process intensification can be obtained based on this enhancement of this interfacial area. Fluidized bed reactor also, there are several applications of this fluidized bed operation, like the drying operation or roasting operations. Whatever, suppose coffee we are getting, that is dust coffee we are getting in our coffee shop, that is actually after several processes. Initially that coffee bean, the raw coffee bean is a green coffee bean, and whenever it will be roasted, and this being done in a fluidized bed, you will see at a certain temperature 400 50 degree Fahrenheit. In that case you will see after roasting of that coffee bean in a fluidized bed, that there will be that mixing of that coffee bean with the gaseous hot gaseous mixture, and there will be particle interactions, and you will see heat transfer will be more important there, and based on that heat transfer, that coffee bean will be becoming that brown coffee bean, and after that it will be becoming dusted and to serve you as a coffee. So, in that case the coffee bean is roasted in a fluidized bed. So, there why fluidized bed is there, why not simply that in a just in a bed just we are heating it, not like that. If you are heating that coffee bean or some other any particles, you can see in a fluidized bed there will be a intensification of process for better heat transfer, better interfacial heat transfer between the solid particles and the gas. So, that is why the fluidization operation over there. Even for mass transfer also in the fluidized bed, you will see for Fischer-Tropsch synthesis there for better contact and better mass transfer, you are just doing that fluidization operation. So, fluidized bed is one also important intensified process in chemical engineering. Rotating packed bed also to get the better contact of the gas and liquid and solid particles, we are having this rotating packed bed. Spinning disk reactor also better mass transfer and heat transfer, this spinning disk reactor important. They are also the making a thin film in this spinning disk reactor so that the mass transfer through the liquid film will be intensified there. So, that is why this spinning disk reactor is important for this chemical engineering process where the intensification is being done. Multi-phase monolith reactor also is important nowadays. They are that some catalyst particles in a particular fashion, in a particular that structure, this catalyst particles will be produced and arranged so that the interfacial area will be more, and then reaction will be better there. So, these are the various process equipments for process intensifications which are being used in chemical engineering processes. And you will see flow based process unit for intensification, like other heat integrated reactions for high temperature millisecond contact time and catalysis also important for this process intensification. Micro engineered reactors are being developed nowadays for chemical engineering processes. Monoliths as biocatalytic reactors are developed for as a process intensification. Membrane separations nowadays are widely used in chemical engineering process for separation of the particles. Even nano sized particles also are being separated by this membrane separation processes. So, this is also one important intensified process. Two phase flow under magnetic field gradients also important there. Applications of ultrasound in membrane separation process nowadays are in research stage to apply for chemical engineering process. Various mechanisms like here slurry bubble column reactors, in that case for creating more interfacial area between phases to enhance the mass and heat transfer. So, slurry bubble column reactor is one important process intensified unit that based on the multi-phase flow system. Fluidized bed reactor are better heat and mass transfer operation of the gas liquid flow are important, and also rotating disk packed bed, in that case better mass transfer, well mixed liquid you can achieve and gas phases, high interfacial surface area, even you can operate it in counter current mode. So, these are the some basic mechanism based on which this multi-phase flow system based process intensified unit are developed for chemical engineering processes. Even you will see compact heat exchanger, like in that case the reducing channel size will give you the better power generation. Even by surface enhancement by metal coated polymer foam for micro power generation, foam heat exchangers are developed, and based on the increase in residence time and better phase mixing, downflow system or inverse flow reactors are nowadays coming to get more contact time, even for more residence time of the phases in the reactor. Membrane distillation is one of the important that integrated system where transport mechanisms are Knudsen diffusion, Poiseuille flow and molecular diffusion. All these processes are simultaneously happens, and the thermal boundary layer is considered to be the mass transfer controlling factor here in this membrane distillation process. Even you will see liquid membrane system also one of the important process where diffusion can be enhanced by liquids then in solids. In that case transport rates several orders of magnitude higher than the solid membranes, because their diffusions in faster in the liquid compared to the solids. Reactive separation also nowadays important, because you know that in fluid system the reaction as well as separation both will be combined in a particular unit, and in that case chemical process industries they are using this they are following this integrated system to have the favorable economics for carrying out reaction and simultaneously with separation for certain classes of reacting systems, and many new processes called reactive separations are carried out, like methyl acetate production. There you will see both that reaction as well as distillation is being happened in a particular column. So, in that case here in this picture it is shown that how methyl acetate is produced in a distillation column. Methanol is supplied and catalyzed as sulfuric acid. In that case the reaction is being carried out in a particular zone. After that whatever products are coming out, those will be separated, that is the what is that methyl acetate and the water to be separated after that distillation also. And so, here this reactive separation is one of the important mechanism of process intensification. In that case combination of separation and the reaction inside a single unit happens. Like some other fatty acid esterification also one of the important this reactive separation process there. So, the reactive separation is important as a process intensification, and reactive separation units you will see may also be treated as a kind of multifunctional reactor in which the functionalities of several processes are combined to generate the new reactor concept. You will see in this diagram there if we are considering that gas and liquid, there may be reactive absorption between that gas and liquid system, and reactive distillation also happens within this gas and liquid system. Reactive absorption also happens this gas and liquid system. Even a gas and solid system, there you will see that the reactive absorption also important, and liquid and solid system, their reactive chromatography, this process is important, and also liquid system, their reactive extraction are the example for that liquid system. So, this you can say that in multi-phase flow systems how different chemical engineering process can be intensified for a particular reaction based on that that combination of unit operation, like reactive separation, reactive distillation, reactive extraction in that direction. And feasibility of the reactive separation, that depends on various parameters like mechanical design, chemical reaction, even separation performance also. So, in this diagram you will see some at a particular temperature and pressure, you will see how chemical reactions are being taking place for a particular process intensification, even mechanical design how it will be giving your that process intensification for that particular operation. So, in this case we can say that any reactive separation process that depends on mechanical design, even chemical reaction performance and separation performance. The most important examples of the reactive separation processes are reactive distillation, reactive absorption and reactive extraction processes. Common feature of that reactive absorption, distillation and extraction are that these processes involve at least one liquid phase, and the properties of the liquid state become significant in that case, and they occur in moving systems. Thus, the process hydrodynamics play is an important role there, because all the process performance depends on the mixing processes, even some other particle interactions, like is there any gas solid particles, if there are gas bubbles and solid particles, even solid and solid, then solid interaction, gas particle interaction, even bubble interactions like bubble coalitions, bubble breakups. If you are having more breakup of the bubbles, you can produce more finer bubbles, so that you can get more interfacial area. Even if your process is the more prone to coalitions, bubble coalitions, in that case performance will be less. So, you have to design a unit in such way that some mechanical provision to be placed, so that the breakage of the bubbles will be there, even uniformity of the bubble flow will be there, or interfacial phenomena will be created in such a way that the uniform mixing will be there, even the distribution of that phases will be there, so that you can get the better performance of the reaction and even processes. So, the properties of the liquid state become also significant there. In that case, what you have to do, that what type of fluid are being used, that whether it is corrosive or not, that also you have to think about it. So, you have to synthesize a solvent which are not that much of hazardous and not corrosive. So, even if it is corrosive, you have to design the unit in such a way that the wall surface of that unit should be non-corrosive. So, the process intensification should be in that directions. So, the properties of the liquid state should be considered for that particular process intensification, and how to control that hydrodynamic cons are there. So, if there is a heterogeneous mixture, to make it homogeneous, to get better performance, you have to make a provisions, like sometimes you know that to reduce the back mixing, you have to use some baffle, or you have to design that unit like 2-dimensional, or you can microstructure system, so that back mixing will be reduced. So, to get that reduced back mixing, you can intensify the process intensifications just by allowing it as a plug flow reactor, because the plug flow phenomena will give you the better performance of the reactions and also other physical operations there. These processes are based on the contact of at least 2 phases also, where these reactive separations or that absorption, distillation or extractions are there. So, for mass transfer through the interfacial area, there of course 2 phases should be involved, and therefore, the interfacial transport phenomena have to be considered for your process intensification. And also further multi-component interactions of the mixer components, a tricky interplay of mass transport and chemical reactions and complex processes chemistry and thermodynamics which should be considered. So, those are involved in that particular process intensifications. Now, let us consider that reactive distillation, some features of that. In that case, complex interactions between chemical reaction and operation, and also if it is there, separations of course will be there based on that complex interactions of the phases, and the performance is influenced by the size and location of the reactive and non-reactive column, and also you know that reflux ratio is one of the important parameters, feed location and throughput by which you can change the hydrodynamics in the column for that reactive distillation system. Like esterification and hydrolysis reactions which are catalyzed by acidic ion exchange resins like Amberylist 15, one of the important you know that resins in which that you know that reactive distillation as well as the separation is being happened in a particular unit. And you will see that reactive distillations where the reactants to be transferred into the reactor and heat integration is important phenomena, and after that integration you will see whenever products are coming out, some unwanted or unreacted products, unreacted reactants to be recycled, and then final products should be separated based on the separation principles. And this successive you know sequential operation of this reactive distillation can be organized here in figure as shown in B. Here that reactants is supplied, and in a particular zone that reaction as well as distillation both will be happened, and at the top and bottom sections that as per you know that density difference and boiling point differences, that products will be coming out or separated, and from the top that product A will be coming out, and from the bottom B that heavy products will be coming out. So, in that particular unit the sequential you can say in the you know in some zone the distillation and reaction both will be happened in that, and after that the distillation process will happen in that particular unit. So, to intensify the process we can say that there is also a need to improve the catalyst and column internals for the reactive distillation applications. And also reaction and distillation takes place within the same zone of a distillation column, and reactants are converted to products with simultaneous separation of products and recycling of unused reactants. And among suitable reactive distillation processes like etherifications, nitrations, esterifications, transesterifications, and condensations and alkylations are the most common applications in reactive distillation process. This operation provides you can say promising processes alternatives to traditional sequential operations for this particular operation. Now, what are those actually advantages for which that reactive distillations are being carried out in a single unit? In this case it is a new you can say less expensive products, even avoiding some hot spots, saving due to smaller equipment you can say, less environmental pollution, higher efficiency because of overcoming the thermodynamic and kinetic limitations, better selectivity to suppressing of undesired reactions. So, these are the some you know that potential advantages of reactive distillation system. In case of reactive absorption, you will see some example here, carbon dioxide absorption in liquid here. Suppose air and carbon dioxide mixtures are being supplied from the bottom of a packed bed reactor. In that case water and sodium hydroxide solutions to be used for liquid, and through that liquid in a packed bed this air plus carbon dioxide mixture will be supplied, and you will see parallelly that reaction as well as absorption will happen when reactions will happen in the packed bed, there will be a product like water and what is that sodium carbonate and water, and along with the air will be coming out from the that top of the packed bed as a clean air. So, during that operation you will see, if we use the sodium hydroxide for absorption of carbon dioxide, there the reaction as well as absorption both will happen. Here reaction will be sodium hydroxide and carbon dioxide will react, and it will give you the sodium carbonate solution, and that sodium carbonate will be used for other application. So, in this case the scrubbing of this carbon dioxide is happened from this air carbon dioxide mixer, and clean air will be coming out from the top of the column. Even absorption of stack gases like sulfur dioxide, gas plus sulfur dioxide mixer, if they are to remove that sulfur dioxide, if you use that calcium carbonate in a solid medium, then you will see that calcium carbonate will react to sulfur dioxide, it will give you the calcium sulphate, and that calcium sulphate will be precipitated, and remaining solutions will be reused, and then carbon dioxide without sulfur dioxide will be coming out as a gaseous medium. So, in that case you can purify that gaseous mixture for the sulfur dioxide or stack gases by this reactive absorption. In this reactive absorption, you will see that reactions occur simultaneously with the component transport and absorptive separation in the same column zone, and it is used for the production of basic chemicals like sulfuric acid, nitric acid, and for the removal of components from the gas and liquid streams. And also absorbers or scrubbers, where these reactive absorptions are being carried out, are often considered gas liquid reactors, and this can be either the cleanup of process gas and streams or removal of toxic or harmful substances in flue gases. So, the reactive absorptions are actually considered both to actually perform like reaction and absorption, and it can be realized in a variety of equipment types here in film absorbers, plate columns, packed units, and bubble columns. And this process is characterized by independent flow of both phases, which is different from distillation, and this will permits both co-current like downflow and upflow, and also counter current operations. So, this reactive absorption you can intensify either by absorber reactors or by designing some other different types of columns like plate columns, packed columns, bubble columns, even intensification of bubble columns in 2 dimensions, 3 dimensions, even bubble columns, downflow bubble columns, even bubble columns with baffles, even some that use of spudgers, even producing more finer bubbles by using different types of spudgers. So, in that direction you can intensify the bubble columns also, and this process can be characterized by that different mode of operation. In that case you can use the downflow system to increase the mixing as well as increase the residence time of the phases, and upflow systems where the first reactions is being carried out, in that case upflow operations is important, where counter current operations also important, where you will see that physical separation or you can say that some mass transfer operations for mineral processing, in that case this counter current operations also important. Reactive absorption represents a process in which a selective solution of gaseous species by a liquid solvent phase, which is combined with the chemical reactions, and as compared to the purely physical absorptions, reactive absorptions does not necessarily require the elevated pressure and high solubility of the absorbed components, because that chemical reaction, in that case the equilibrium state can be shifted favorably, resulting in enhanced solution capacity there. So, we can say that most of the reactive absorption processes involves their reactions in the liquid phase only, and in some of the cases both liquid and gas both will be taking places in the as a medium. So, the medium also, the mode of operations and discretizing the system, discretizing the medium also sometimes way of the intensification of the process. Now, in reactive extraction, in that case reaction as well as extraction both will happen, and this reactive extraction uses liquid ion exchangers that promote a selective reaction or separation. And the solutes are very often ionic species like metal ions or some organic or inorganic species, or you can say some intermediates like furfural, phenols, etc. These can be used for separation and purification, or you can say that enhancement of the conversion of units for the conversion of salts in the units there. Like for biodiesel processes, they are a combination of this extraction of oils using a solvent with the esterification reaction that will give you yield of fatty esters, that is called biodiesel. So, the reactive extraction is the process intensification by which you can produces the biodiesel there. And liquid extraction is sometimes based on the partial miscibility of the liquid. So, you have to derive some liquids where that immiscibility will be there, but separability capability of that liquids will be enhanced there. So, both the way you can increase, so immiscibility as well as that that absorbance of the contaminants in that particular liquid should be increased. In the simplest extraction system, two compounds have to be separated there, and this can be done by extracting with a carefully selected solvent in which one compound, that is called solute, easily dissolves, whereas the others does not. Like as an example, you can say that like propionic acid to be actually separated from the liquid water, or you can say waste water in a that paraffin or like octanol or decanol like organic compounds. In that case decanol and this water is immersible, and propionic acid is miscible with water. So, from the water, this mixed propionic acid to be separated by that decanol, and so this decanol and water should be immiscible, and also there should be a selectivity based on the boiling point also. You have to use the organic compounds which have the boiling points which are higher difference in with the that propionic acid, so that after that extraction of that propionic acid in a decanol as an example here, which is to be separated by just distillation. So, in that case you have to select the organic solvent in such way that where this compound or contaminant in the liquid can be easily that transferred to the liquid medium, which will be immiscible in the that continuous phases. So, based on which that immiscibility these two liquids will be or organic liquids will be produced as a droplet form, so that you can get the more interfacial area through which that mass transfer, or here in this case as an example that propionic acid to be transferred through the interface of this liquid to the that decanol or paraffin, some other organic liquid. So, this is the mechanism by which that liquid extraction being happened, and in that case most important that you have to select the suitable solvent where that you can produce the droplet, and you can easily separate those compounds after that extraction of that contaminant. And also it is related to the droplet phenomena that I told, that if you produce that droplet, if you are producing more finer droplets, you can get more interfacial area, so that your that extraction will be more, and process efficiency will be more mass transfer will be there. So that is why this reactive extraction process, that depends on your design, and how it can be designed, how to produce that more finer droplet, how to select that solvent. So for that, to produce the more finer droplet there, you have to design some unit like mixer settler systems, you have to use some mechanical provisions, so that more turbulence will be there, more interfacial area to be produced by producing droplet. Column extractions to get the more interfacial area between the liquid and liquid, so that you can have more extraction. Even sometimes centrifugal extractors also are being developed for process intensification for this extraction. In that case, centrifugal action, centrifugal force will be applied to separate those liquid contaminants into another liquid by just action of gyration, and also making a thin film of that liquid, immiscible liquid, so that through that thin film, that mass transfer will be more efficient. Counter current column extractors can be further subdivided into that non-agitated, non-proprietary columns and agitated proprietary extractors. In that case, you will see sometimes that counter current operations are being used there to actually design economically, so that without making a droplet, how you can increase the efficiency of the extraction. So in that case, you can save some energy, and also that easier to handle those operations. So that is why counter current column extractors are also one of the important intensification of this extraction process. So the extraction process, you can say that various forms of energy inputs are required, like rotation of propellers, impellers, disc propulsion, and also that pulsation process, even vibration and ultrasonic devices and centrifugal devices. So to run those equipments for this process intensification of extraction, you need various forms of energy. And agitating the liquid system that breaks into droplet, to use this energy, you can increase the droplets, you can increase the interfacial area, so that you can get the better mass transfer of extraction. And also if you increase that droplets by this energy, you can increase the interfacial area to improve the mass transfer and column efficiency. Another important intensification process of multi-phase systems are development of the micro reactor, micro channel based heat exchanger. In the case of micro reactor, multi-phase based micro reactor, in that case they have some potential for the rapid heat and mass transfer. The enhancement of this transport processes is related to the decrease of diffusion paths on the micro scale phenomena. For fast multi-phase reactions, these are very important, and the rate and selectivity of the chemical process that can be greatly influenced by the transport of these reagents within the phases. And here as shown in figure, some micro channel based reactor, where the porous catalysts are being used, and the microstructure packing, in that case through that packing there will be a reactions as well as mass transfer and heat transfer will be there. So to increase that interfacial area, these microstructure reactors are being developed, and in which that enhancement of the transport processes are taken place. And variety of different purposes also are fulfilled based on this the application and requirement of high heat and mass transfer coefficients in the micro reactors. And also in the micro reactors, we are getting that well defined flow patterns, and because that heterogeneous flow patterns, sometimes their back mixing are being used, are actually seen in column reactors. There to avoid those back mixing, so micro channel based slug flow pattern or plug flow patterns are that devices. So, that mechanism are being used for process intensification. And the spectrum of the applications includes gas and liquid flow as well as gas liquid or liquid liquid multiphase flow systems in this micro reactor system. So, why this intensification from macro to micro reactor? So, when comparing the process in micro reactors with those in conventional systems, a few general differences can be identified, like flow in microstructure is usually laminar in contrast to the turbulent flow patterns on the macro scale, and the diffusion paths for heat and mass transfer are very small, making micro reactors ideal. And you can say that for heat and mass transfer limited reactions which are very convenient for in this particular micro reactors. The surface to volume ratio, of course, in this microstructure reactors are very high, and thus surface effectives are likely to dominate over that volumetric effects. The share of solid wall materials is typically much higher than in microscopic equipment. Thus, the solid heat transfer plays an important role and has to be accounted for when designing that micro reactors. And using like silicon microfabrication, it is possible to construct packed bed micro reactors that provide a 100-fold or more improvement in mass transfer for gas liquid heterogeneously catalyzed processes such as hydrogenation of unsaturated hydrocarbons. That is actually reported by Losley et al. In 2001. They have done this hydrogenation of unsaturated hydrocarbons in multi-scale multi-channel micro reactor. And in these devices standard catalyst particles 50 to 75 picometer diameters are retained in silicon channels by an integrated microfabricated filter unit, especially designed gas liquid inlet section with narrow channels provides that rapid contact of the gas and liquid reagents. Now, in order to achieve those uniform flow in that micro reactors, you will see that pressure drops in the inlet gas and liquid sections that will be higher than those in the individual reactor channels. So, though it has the higher pressures, still it has some advantages to get the more efficient reactions. The small particles provide the high surface area for improved gas liquid mixing, but they also represent a challenge in terms of pressure drop and fluid distribution among the parallel channels. And the pressure drop can be reduced by replacing catalyst bed by a microfabricated support structures there. And uniformity of the structured packing arrangement also important. In that case, you can control over the fluid flow, that is by this structured packing arrangement, and that will give you the enhanced relative to the micro packed beds condition, and the activity is greatly enhanced if the catalytic component which is supported upon a porous layer and formed by making the silicon posts porous, and in that case direct fluorination as an example that can be served as an inspiration for development of flow distribution, allowing controlled scaling of gas liquid reactions from a few channels to a large number of channels like 100 micron channels with uniform flow distribution at a flow regime of plug or liquid segments. Another important intensification by changing the geometry of the channel. In some cases, for example, when large residence times are desired, in that case you will see that comparatively long micro channels are have to be integrated in such a way that it will be made a curve shape, and it will be made a curved channels, and in addition to this straight channels are often not suited for connecting a microflow domain to the external world, so that you are making that curved flow, and also whenever you are making a carb flow, there will be a creation of secondary flow, that is called Dean flow, due to the curve perpendicular to the main flow direction, which will be induced by the inertial forces, which is the main factor for the process intensification. And the typical secondary flow pattern in curved channel is given by two counter rotating vortices separated by the plane of curvature. The strength of these vortices increases with increasing Dean number, where that this factor k, that is Dean number, will be represented by the Reynolds number into root over of dH by r, where dH is the hydraulic diameter of the curved channel and r is the mean radius of curvature of the channel. So, some other intensified unit like micro heat exchanger development, in that case you will see that the design of micro heat exchanger, where the goal is to often to increase the heat flux while limiting the pressure drop, and also for that for some pumping power or pressure drop, a considerably higher heat flux is achieved in the curved channel. So, in that direction the curved microchannel based heat exchanger are developed. And other intensification like ultrasound cavitation, application of ultrasound in processing and synthesis are widespread and often unusual and beneficial operating conditions. Two major principles are used in sonochemistry, like mechanical effects of mixing and disintegration, high energy process for radial reactions. Most effective process, like in that case sound pressures sometimes develop to produce that cavitation to get the more interfacial area. So, in that directions this ultrasound cavitation is produced to get more interfacial area and more mass transfer there. So, we can classify that range of applications of ultrasound process based on different multi-phase systems like chemical and physical effects of ultrasound, here homogeneous systems, liquid and gas systems, CUS treatment, sonolysis, nanoparticles, even novel materials, liquid systems like emulsification, extraction, CUS sludge, even phase transfer catalysis, mixing, etc., liquid solid like cleaning, crystallization, extraction, dissolution reactions, etc. So, in this lecture we have then gone through what actually that what are the different mechanism of different process intensification of the chemical process which are being intensified for particular process systems, and different mechanism which are involved in this process. So, I think it will be helpful for further understanding of the process intensification in chemical engineering processes. So, I would suggest you to go further reading with this suggested books for this further understanding of process intensification mechanism for various application in chemical engineering process. So, thank you.